Hey everyone, Mr. Hood here. Get ready, because the pace of AI innovation is accelerating, and we're breaking down everything you need to know right now.
Welcome to Tech Talk with Mr. Hood. I am Larry Hood, and today is AI Update, what we learned in 2025, and what it means right now. This isn't a hype recap. We're breaking down what's real, what's next, and what skills and decisions actually matter. We'll talk politics, the global AI race, jobs, chips, and even a real case study of an AI-designed drug in trials. Let's jump in. First, I want to start with a question. Quick question. If an AI can sound empathetic, does that mean that it's empathetic? It does not matter. And does that matter for the future we're building? Hold that thought. Let's set the stage.
Away from when the model is doing most, maybe all of what SWEs do end to end. And then it's a question of how fast does that loop close? Not every part of that loop is something that can be sped up by AI, right? There's like chips, there's manufacture of chips, there's training time for the model. So it's, I think there's a lot of uncertainty. It's easy to see how this could take a few years. It's very hard for me to see how it could take longer than that. Yeah. But if I had to guess, I would guess that this goes faster than people imagine, and that key element of code and increasingly research going faster than we imagine, that's going to be the key driver. It's really hard to predict, again, how much that exponential is going to speed us up.
You demos were a little more cautious last year. You said a 50% chance of a system that can exhibit all the cognitive capabilities humans can by the end of the decade. Mm-hmm. Clearly in coding, as Dario says, it's been remarkable. Mm. What is your sense of, do you stand by your prediction? Yes. And what's changed in the past year?
Yeah, look, I think I'm still on the same kind of timeline. I think there has been remarkable progress, but I think some areas of kind of engineering work, coding, also you could say mathematics, are a little bit easier to see how they would be automated, partly because they're verifiable what the output is. Some areas of natural science are much harder to do than that. You won't necessarily know if the chemical compound you've built or this prediction about physics is correct. You may have to test it experimentally, and that will all take longer. So I also think there are some missing capabilities at the moment in terms of not just solving existing conjectures or existing problems, but actually coming up with the question in the first place, or coming up with the theory or the hypothesis. I think that's much, much harder, and I think that's the highest level of scientific creativity, and it's not clear. I think we will have those systems, so I don't think it's impossible, but I think there may be one or two missing ingredients. It remains to be seen how, first of all, can this self-improvement loop that we're all working on actually close without a human in the loop? I think there are also risks to that kind of system, by the way, which we should discuss, and I'm sure we will. But but that could speed things up if that kind of system does work.
We'll get to the risks in a minute, but one other change, I think, of the past year has been a kind of change in the pecking order of the race, if you will.
Okay, what do we mean when we talk about the foundation? What do we mean when we're talking about comparing AI intelligence to human intelligence? What do we mean by that? AI versus human intelligence. Why ethics first? I mean, really think about it. You think about mass surveillance, you think about all the things that can happen. And when people compare to human intelligence, their main instinct is to focus on speed, scale, memory, and pattern recognition when you think about artificial intelligence, but there's more to it. And so before I get started, I want to talk about myself. I am Adobe certified professional, also in the Generative AI Foundations by Pearson, recently certified, and also in prompt engineering, ChatGPT certification, and I am an ICT credential CTE teacher in the information technology sector, as well as arts, entertainment, and design. And I am a teacher of advanced placement, computer science principles, game design 1 and 2, community schools council member, Skills USA advisor, and also an educator and researcher and public speaker in AI and emerging technology. So back to the topic. What do we mean? Okay, I'm talking about AI versus human intelligence. In this slide, I borrowed some of the stats. I like to look at Dr. Alan Thompson, some of his research work. He has a lot of great statistics. And so from this, I wanted to illustrate why do people compare human intelligence and the instinct. And it's kind of messy when you really think about it. This is the part that gets messy. Humans don't just calculate. We care, we justify, we feel responsibly, and we live with the consequences. So this slide illustrates a test that was done by Microsoft and Meraki, and it was done on the large language model ChatGPT-4 back in 2022. As you see here, there's a IQ score and an ethics score, which I'll touch on in just a minute. And as you see, they looked at some of the human gifted versus the previous versions of ChatGPT, and they developed an ethics score that is based on a defining issues test. And this was done by Microsoft and Meraki. You can check it out. And so this paper examined moral sensitivity in exceptionally intelligent children, and it also compared those and drew some parallels about certain abilities in ASI, which is super intelligence. And so what he says is, by highlighting how advanced intelligence fosters goodness, it offers reassurance that smart systems lean toward kindness and fairness, easing fears about our AI evolution. And I tend to disagree with that. I don't think just because a model becomes smarter that it becomes more fair and more ethical. And you'll see why. So this is a cross-sectional study in a non-identifiable database on Reddit, which is commonly used to draw 195 questions from verified physicians' responses to public questions. And so from these responses, they basically did it within a couple of days. An original question along with an anonymized and randomly ordered physician and chatbot responses were evaluated in triplicate by a team of licensed care professionals. And so they chose which responses were better, judged them both on quality, and for very poor, acceptable, good, very good, and which ones were actually empathetic. And so this leads me to when you talk about geopolitical battle as well as a corporate battle for market share. And this is when you talk about the marketing dollars that go into it and some of the promotions that go into it to try to get more users on the platform. Which brings me to the move toward ASI, super intelligence. And so what I was looking for is how are they going to label something as super intelligence? And we're at the precipice of AGI. AGI is here, artificial general intelligence, where any AI is smarter than any human. Now we're talking about super intelligence, and what does that mean? And from my perspective, I see a lot of study, a lot of research focused in the area of moral measurement, and that's what we're going to look at today to figure out how are we using, a moral measurement, which is done on humans, to apply this to an AI platform. The future of the industry. So this is kind of like my overview. I feel that AI is shifting from experimentation to large-scale development across all sectors. You got media narratives that focus on hype and durable value, jobs, skills, and regulations. And the next decade, for me, will be shaped by compute policy and how fast organizations can adapt. But like I said, it's really messy, okay? And this is the part that gets messy because it's values. Humans don't just calculate. We care, we justify, we feel responsibly, and we live with the consequences. So now if an AI system becomes dramatically more capable, the real life question becomes, do we get more safety or do we get more risk? And here's why. I'm starting with ethics. The next decade isn't about models. It's about deployment inside of schools, hospitals, workplaces, and public systems. That's where values show up. Can machines have empathy? I don't know. What do you think? I don't think so. Let's define the question clearly. We're not asking whether a machine has human feelings. We're asking whether an AI can produce communication that people experience as supportive, respectable, and helpful. One of the most cited early studies compared clinician responses with AI chatbot responses to patient questions in a public forum. Evaluators rated chatbot responses as more empathetic and higher quality. But an important caveat is that AI responses were often longer, and the setting wasn't a real clinical workflow. So the takeaway isn't AI replaces doctors. The takeaway is AI can draft, humans must supervise, and oversight is the difference between help and harm. You know, it keeps exploring empathy, perception, and different ways you can prompt the AI, showing a topic is still advancing and still active and still evolving. And so this leads me to what I'm talking about today, which is the moral question and how they're doing that. And this is a formula. It's called a P formula, defining issues test. It's just a probability. Okay, it's based on a number of post-selected conventional options. And post-conventional really just means an adult way of looking at different questions that around some kind of dilemma. Okay, and that's what this is, and this is all it is. And so when you're talking about the behavioral test, this is something used in psychology that is primarily used for kids who are of age and testing their moral judgment. They look at 4 principles, components: moral sensitivity, judgment, motivation, and character. And so ethical behavior requires all 4 components. Failure at any stage can prevent a moral outcome, even if someone knows the right thing to do. So, more research needs to be done. But to talk about ethical behavior, we need language for how moral reasoning develops. One common framework is this framework, which is Kohlberg stages, from rule avoidance to reward, across 6 stages from rule avoidance, reward seeking to law and order reasoning and principles. One of the widely used tools in moral psychology is the defining issues test. The DIT or DIT2, it measures how people prioritize different kinds of moral reasoning when faced with dilemmas. And here's the key limitation though. Moral reasoning is influenced by culture, context, and lived experiences. So when we talk about ethical AI, we're not plugging into a perfect scoreboard here. We're building systems that reflect human choices. Even the tests themselves get audited for bias and consistency across groups. For example, studies validating versions of the DIT instruments across gender, political, and religious affiliations. So we're looking at this as a way for me to simplify for people and educate people on AI, explain my research findings and current revolutionary progress in artificial intelligence, and then move towards superintelligence and what that is. So I have several things I wanted to talk about, and the ethical foundation here are the major forces for me that's shaping AI in 2026. For number 1, we got a bubble or transformation. What does that mean? Okay, yes, there is hype, but the real question is, where is durable value being created when you talk about durable? For me, I look at, if you're going to talk about durable transformation, you're going to have to look at least one of these things has to happen, okay? Number 1, it has to reduce time. It has to improve quality. It has to lower error rates. Or you're creating something, that you're capable of, but you couldn't simply do before, okay? So at least one of those things have to exist for you to call it a durable transformation, okay? And the winners won't be determined by only a product. They'll be shaped by geopolitics and infrastructure, okay? And that's when we're talking about the global AI race. AI is now strategic infrastructure. We're talking about chips, data, talent, energy, and supply chains. And when we look at this next slide we're going to talk about the global supply chains and the different regions that emphasize different priorities. You have innovation, speed, national security, safety, privacy, and the industrial policy. How does that look across the board? And what strategy shows up in regulation and executive actions as you see here? Because this slide here, again, I borrowed from Dr. Thompson. It has ASI and it shows different methods in orange that have partially been achieved with AI, and then the ones in green have been totally achieved. If you see, there's quite a few things we're looking at for phase 1, phase 2, and then phase 3. And we have quite a ways to go when we talk about ASI. So when we look at geopolitics and infrastructure and our pipeline, lithium-ion batteries are a global supply chain. The 1980s discovery of lithium cobalt oxide enabled today's lithium-ion batteries powering phones and EVs, electronic vehicles. But the key ingredients come from a geopolitical concentrated region, creating supply risk and choke points. And this is based on a U.S. Geological Survey, where the critical materials come from. Where does all this stuff come from to keep pushing this, this race for global AI supremacy? We're looking at cobalt. It's a cathode ingredient, and it dominates the market. It's 76% of the world's output of cobalt comes from the Democratic Republic of Congo. Okay, and then you have 10% of it from in Indonesia, and then China leads in refined cobalt, and then the major mine output of the world comes from Australia, Chile, China, Argentina, Zimbabwe, among others. And for the U.S. and lithium imports for 2020 and 2023, that came from Chile and 47% from Argentina. So as far as the race in geopolitics, you have U.S., China, treating AI as strategic infrastructure. You got national strategies, you have export controls, subsidies reshaping the landscape. Companies are choosing research and development locations based on regulation, talent, and the compute access. China and the European Union update, the key differences are China focuses on rapid deployment to boost industry and state capability, and the EU is prioritizing human-centric approach, attempting to balance innovation with strict regulatory guardrails. For job skills and the labor market shock, the media is framing jobs as a loss to job transformation. Many roles will be redesigned around AI tools and workflows. Reskilling and continuous learning become economic priorities. You gotta keep upskilling. You gotta learn new things because it's really important. And also our phones, is creating a profile of you. This is what you would call, when you talk about NPUs, neural networks, agentics, AIs, employees. So it's autonomous. We have autonomous agents that coordinate tools, workflows, not just chatbots. So organizations are piloting AI as digital co-workers for drafting, coding, analysis, and this raises questions about oversight, reliability, and human AI collaboration models, like who owns the data? What are we talking about here? Okay, and you see executive actions and policy and frameworks trying to balance innovation with safety. For a widely cited U.S. reference point, Executive Order 14110 from October 30th, 2023 laid out a major federal priority around safe, secure, and trustworthy AI. And it is heavily analyzed in federal policy summaries. So there's a lot going on. And one of the things I want to illustrate here with this slide is this presentation tonight was inspired by my attendance at the Future Forum, the use of AI to advance healthcare. And it was given by Dr. Thomas Parham, where I actually was in the forum. I actually, discussed several topics. We looked at AI-driven healthcare innovation. We looked at workforce transformation, education alignment, equity and access in the AI era, trust, ethics, and community empowerment. Cross-sector collaboration for systematic change. Several speakers were there, very many great speakers that were there. And I thought it was very impactful to me. And I wanted to share that, and this is kind of just letting you know this is kind of what spearheaded tonight's presentation. So one of the things that came up was something called Ambient Scribe, which I'd never heard of before, but it's an AI chatbot that is emerging in the medical space, healthcare space, that doctors are using, it listens to everything it's saying to its patients and initiating electronic health records, okay? Writing all the notes, so saving doctors time and administrators time when it comes to healthcare. In a lot of areas, a lot of different places and hospitals cannot afford this type of technology, but it is a very valid and strong technology that's being used in healthcare and also in other areas in mental health as well. So let's talk about chips. I wanted to talk about chips because there's a lot going into this. You know, we talk about chips, but agents don't just answer questions. They chain tools together. They coordinate steps, and they execute a workflow. Okay, so that's a powerful and risky. So the governance questions become: who approves the actions? You know, what gets logged? How do we audit the decisions? You know, what's the rollback if, you know, something goes wrong? Okay, all of this runs into a hard limit when you talk about compute chips, you know, the bottleneck, you know, the microchips. You know, there's a lot going on. GPU, data center, massive investments, you know, energy efficient data centers. You got who's going to get control of the advanced fabrication and supply chains, you know, and this becomes a source of strategic power. So you can look and take a step back and look at what's really going on in the world when you talk about some of this stuff and the race towards strategic power for some of these things that are occurring right now. And so what I wanted to do was kind of talk about, you know, some of these things here as far as chips.
From sand to silicon to a wafer, layer by layer, it becomes the chip, CPU,
From
GPU,
sand to silicon
and
to
NPU.
wafer, this is how a CPU becomes a chip. Okay, you got sand, silicon, then it gets pure silicon, then it gets turned to a wafer, and then that's how it gets put into a chip. And then the other thing I wanted to illustrate is this slide.
This microchip can take up to 26 weeks to make. In its as many as 100 layers, billions of transistors are packed into an area about the size of a fingernail. They're the brains behind almost everything we use in our increasingly electronic world. Here's how these complex, tiny devices are made. The process begins with silicon-rich sand. Why silicon? Silicon is a semiconductor. It's the sweet spot between an insulator and a pure conductor. That means its properties, such as its conductivity, can be altered by adding impurities or doping to meet the needs of different electronic devices. This also allows us to control the electrical signals that pass through. Silicon is also abundant. It's one of the 10 most carbon and melted in crucibles to produce carbon monoxide and 99% pure silicon. After further processing, ultra-pure silicon is produced. Next, a seed crystal is placed in contact with molten silicon. As the seed crystal is slowly pulled away, silicon atoms are deposited on the bottom surface. The result is a large cylindrical boule, or a single crystal ingot of pure silicon. The boule is then thinly sliced into wafers. Silicon wafers typically have diameters of 1 to 12 inches, with the most state-of-the-art facilities being able to produce wafers up to 18 inches in diameter. Bigger wafers are, of course, able to yield more microchips. Once the silicon wafers are cut, the production process begins in full. Microchips are made in extremely sterile conditions, free from contaminants such as dust. If even just one particle of dust makes its way onto a silicon wafer, the entire batch is at risk of being ruined. This would derail a process that can take an average of 12 weeks. The first step of the production process is deposition. A thin, non-conducting layer of silicon dioxide is grown or deposited on the surface of the wafer. Then the silicon wafer is prepared for lithography by coating it with photosensitive and light-resistant materials. The next step is very critical: exposure. The prepared silicon wafers enter a lithography machine. and are exposed to UV light passed through a reticle containing the chip's blueprint. The areas exposed to light are hardened, while unexposed areas are then etched away by hot gases to leave a three-dimensional microchip. The electrical conductivity of different parts of the chip can also be altered by doping them with chemicals under heat and pressure. This process can be repeated hundreds of times for the same chip, producing a more complex integrated circuit at each step. To create conducting paths between the components, a thin layer of metal, such as aluminum, is overlaid onto the chip, and the etching process is used to remove everything except the thin conducting pathways. Several layers of conductors separated by glass insulators can be laid down. Each chip on the wafer is then tested for performance before it's separated from other chips on the wafer by a saw. Since microchips are essentially circuits built on an incredibly small scale, they have a basic set of components. Capacitors can temporarily store an electrical charge. Resistors help control the electrical current. Transistors can either amplify or switch the electrical signals passing through. For more advanced chips, like those found on high-end graphics cards, there can be upwards of 28 billion transistors on board. More transistors on microchips allow them to send out more instructions, increasing the computational power. Moore's law predicts that computer chip manufacturing would advance at a steady rate, allowing transistor counts to double every 2 years. Based on the sheer power of the technology we use on a day-to-day basis, this decades-old prediction seems to still be mostly true. Manufacturers have been shrinking down their transistor sizes to fit more onto chips. Each breakthrough in transistor size has allowed the production of more powerful chips for our phones, computers, and gaming consoles. In recent years, they've gotten each transistor down to as small as 8 × 10 to the power of -8 inches in diameter, allowing an amazing 50 billion transistors to be crammed onto a single chip. Manufacturing microchips is truly one of our most complex feats, and yet innovations are happening every day.
So that's how chips are made. So I wanted to share that with you. Very important to know. And I would be remiss if I don't talk about Mark Dean, the chief engineer at IBM. In the 1980s, he led the team that created the first IBM personal computer, the PC, and later developed the very first gigahertz chip in 1999. So in honor of Black History Month, I definitely want to talk about Mark Dean. Appreciate your work, and definitely a pioneer in the game. He is definitely a living legend. If you never heard of him, look up Mark Dean. So in terms of where we're at now, next-gen processor transition, you got Intel Core 9s, which has a more monolithic design with the memory separate. And now we have more modern chips where it's a tile-based system, and you have SoC, which is system on a chip architecture. So you have more memory coming from the actual chip itself, and less memory in the separate DRAM modules. You're starting to see some of that in some of the chips with more memory built into it, into the NPU. So this leads me to Intel Core Series 3. Intel Core Series 3 is a new chip, new architecture. It's in its 3rd generation. And this is the look of the chip, more rectangular graphics, input-output tile, a compute tile. And what's different from the previous chips is its tile, the way it's set up. In the previous chips, it's just one slab of silicon. This one is broken into different tiles. And what this does is it just kind of is a shift towards AI integrated computing, dedicated NPUs on the chip for more efficiency, performance, key upgrades. Graphics are faster, 76% higher in Series 3, a lot more power. Your batteries are going to last longer, and really good for gaming and content creation. So this was just introduced. This is the Core Series 3. So if you look for a laptop right now and you're trying to get something that's the latest chip technology, look for something that has an Ultra Core Series. 3 or Series 2, which you probably see on the market. But some of those earlier chips are going to start getting phased out, and what you're going to start seeing is more laptops and handheld mobile devices being shipped with these chips, these NPU chips, or chips with an AI core built into it. And so this is what it looks like. This is the new form factor. You know, it's more rectangular look, and you have a lot more integration in the motherboard. You know, you have partner chips built into the motherboard that work with the processor. So it does actually look different, the shape of it, for those of you who are into that kind of thing. And so with this slide, I want to talk about data sets. You know, if you're making your own model, or if you're trying to understand how this stuff works, and AI, where is it getting its data from? You have different data sets. And you have different companies that have their own data sets. But in the general terms, when the study was done for GPT-3, the data set, you have stuff coming from some of these types of websites and different things. And so there's a lot of information on this. And so one thing that I want to talk about the chip, though, is that on the chip side, we're setting a new processor generations marketed directly around AI acceleration. So the Intel Core series is one definitely, you know, that is leading the way on that. And so when we talk about data sets, you have more data than ever before. And then when you have more chips with NPUs on them, you can actually kind of have a open or closed model based on what your chips are doing, okay? What kind of architecture that you have, okay? When you have an open models expand access and innovation, and I would say a closed model can be easier to secure and govern, okay? But most organizations will end up with some kind of hybrid. So a closed system for sensitive work and open tools for education, prototyping, and community innovation, okay? So, but when you look at this slide, you see where a lot of these types of data sets are coming from. You got it categorized like code, government, legal, Wikimedias. You have academic side, public domains, books, all these educational resources. And this is just a breakdown of different types of data sets that would go into some of these models. In this slide here, I'm looking at what Microsoft used as far as its research study and probing in the moral development of large language models. Okay, so this is the archive paper that was done recently. You can kind of look at this. It was called the Probing the Moral Development of Large Language Models Through the Defining Issues Test. And I spoke on that earlier, but I want to just kind of give you guys this for reference so you can see what I'm talking about here. And so in terms of the Defining Issues Test, it's really consists of 5 different scenarios involving complex, real ethical dilemmas. After reading each scenario, respondents answer, following type of questions. The action choice question, like you're asking a question, what are the main characters should do? Like, should he steal the drug to take care of his wife? Or some kind of ethical question about that. Then they rate the task, and then they rank the task, the key focus areas. It's going to test whether a person prioritizes personal interests, maintaining norms, or some type of post-conventional thinking around universal principles of justice. So it's a really interesting test when you look at psychology, but for me, in my opinion, I don't think this really applies to an AI, a large language model, because this test, Defining Issues Test, it's based on a principle for toddlers who are in the formative stage in education and dealing with humans. So I don't think you can really look at that. And so Kohlberg's theory is that moral development progresses sequentially through stages. However, an important aspect to note is that progression is not automatic or guaranteed. Factors influence progression include cognitive development, social experiences, lived experiences, opportunities for role-taking and moral discourse. So his work emphasizes the importance of providing children with the opportunities to engage in moral reasoning and decision-making. So this approach has significant implications for early years in education of kids, so encouraging educators to foster environments that promote moral growth and ethical thinking and community decision-making. So that's kind of where the development of this came from. But in my opinion, it has a lot of contextual limitations. It neglects cultural variations. The theory does not fully account for how different cultural values shape moral development. For example, in collectivistic cultures, moral reasoning might prioritize group harmony over individual rights. A perspective that's not well represented in Kohlberg's stages. So, in my opinion, not really good to use this as a measurement on an AI. So the ongoing debate, when we talk about open and closed models of AI and safety, open models for innovation, closed models for safety and control. Governments explore AI safety standards, testing, and reporting requirements. The future ecosystem may depend on how openness versus risk is balanced in regulation. So you're looking at creator economy and synthetic influencers. AI-generated influencers and virtual characters gain a large audiences, and it's getting bigger and bigger every day. And so brands are experimenting with, different synthetic spokespeople, fully generated campaigns. Media also covers concerns over authenticity. You got disclosure, audience trust or distrust. I mean, there's a lot going on here when you talk about influencers. Virtual influencers scale content fast, and they stay on brand, and they operate nonstop. I mean, brands like to control, audiences worry about authenticity, though. So you got to really think about if you're a company using these influencers. And this is an illustration of some of these types of influencers that are out there. These are all virtual, and you may recognize some of these, but this is what I'm talking about when you're talking about virtual influencers and generative AI and some of the things that is gaining ground in the market. And then you have AI chatbots at work, and you have, you can clone some of the workflow that you do with an AI, so you have like a co-pilot or a clone of what you do. And so in AI, when you're talking about education and reskilling, this is a big one. This is a big one because governments and firms highlight AI literacy as a foundational skill. So upskilling programs emphasize data literacy, coding, and prompt design, and they're complementary to human skills, creativity, judgment, collaboration. All that stuff is going to grow in value. So when you have an awareness and understand how these things operate, that's going to help make you more of a valuable employee, and you'll be able to collaborate. And so with this slide, I want to just kind of illustrate some ethical guidelines for some of this stuff. AI can be a valuable learning tool when used the right way. So do use AI for learning. It's like having a smart study buddy. Do be critical of AI-generated content. Double check the trusted sources. Do keep personal info safe. Don't share too much info with AI. Do ask questions and seek assistance when needed. So the wrong way, I would say, is don't use AI to cheat or engage in dishonest practices. Don't use AI to spread misinformation. Don't overly depend on AI for learning. It's a helper, not really a replacement. And don't accept all AI-generated content as accurate and truthful. So on this slide, I want to talk about spec-driven development. And you have, a different way of looking at it. You just don't write one big, large prompt. You want to specify what you want and why. That's a prompt. Then you validate. Then you want to plan. You want to plan how you want to build it. You literally tell plan how to build this, and then you're going to validate. You're going to validate it. Okay, you're going to validate it because one of my sayings always: you never want AI to operate in a place where your brain is supposed to think. Okay, that's my saying. Tell that to my students. So you want to always validate. Once you do that, then you're going to go into tasks. You're going to come up with tasks. You're going to validate the task. Okay, and then you're going to implement, execute, and verify. So these are some of a specific spec-driven way of developing something you're building with AI, just to kind of guide you on that task. And so this slide I want to talk about is software engineering and where we're at today. We have tests that was done. Claude Code and OpenAI Codex have graduated from autocomplete to project-scale autonomy. Cursor documented agents running a 3-week session over 1 million lines of code on single projects. One agent migrated an entire code base, 266,000 editions 193,000 deletions without human intervention between checkpoints. Now, what am I saying here? Okay, basically what I'm saying is when it comes to software engineering and just writing pure code, this is the breakdown for accuracy. As you see, Claude Opus 4.5 and ChatGPT 5.1 Codex Max were the most accurate when you're talking about where we're at as the status of current models writing code and the accuracy of them. So as far as Gemini's great. It's about 76% accurate based on this study. And as you see, Claude and ChatGPT 5.1 are in the lead at this time. So what does this mean? Concentration of power versus democratization. Top AI labs concentrate compute, data, and cutting-edge talent. At the same time, smaller and open models lower the barrier for entry. So anybody can create their own model. The future may be a hybrid, though. Powerful centralized models plus a wide variety of available local tools, which is kind of happening now. You see a lot of companies, huge corporations battling for market share. And then you have a lot of independent developers making a lot of platforms and things that you can use, but they don't get a lot of marketing share, a lot of marketing dollars to promote, so they even exist. Now, this slide here I wanted to illustrate is what Donald Trump actually implemented back in November. This was called the Genesis Mission, okay? And if you never heard of it, take a good look. What is it? What is the Genesis Mission, okay? It's basically was created, they're creating their own model. And so our government's creating its own model. And so what we have is we're having implications and strategic questions around this. Where will sustainable value emerge as the hype cools down? How will the chips and talent pipelines shape competitive advantage? What mix of human skills and AI capabilities will your organization prioritize now? I mean, there's a lot happening and some stuff people are aware of and not so much, okay? But this is the order. Executive Order 14363, November 24th. Okay, what is it? It's a dedicated, coordinated national effort to unleash a new age of AI-accelerated innovation and discovery that can solve the most challenging problems of this century. The Genesis mission will build an integrated AI platform to harness federal scientific datasets, the world's largest collection of such datasets, develop over decades of federal investments to train scientific foundation models and create AI agents to test new hypotheses, automated research workflows, and accelerate scientific breakthroughs. And yes, I'm talking about all of the major platforms, Claude, OpenAI, Meta, XAI, all these things are all working towards this Genesis mission. So something we all need to be aware of. And this brings me to my next slide here, which is an AI designed drug nearing late stage trials. Now, this is not a United States trial. This is something that was done by China. This is really important because this is the first AI designed drug that was done totally with generative AI. Okay, so what we're going to look at here is a clinical study. It's the first clinical study of its kind, and the case study was on a drug called Rentosertib for idiopathic pulmonary fibrosis. What is that? Well, what that is just scarring of the lung. Okay, so it's a drug to help that. Okay, they call it the first-in-class small molecule inhibitor developed for IPF. Okay. AI was used for target discovery and prioritization and generative design of a small molecule, okay? And what led to that is lab and clinical work followed by standard practice. So what they did, they took 128 patients and 71 of them passed and are in a phase 2 clinical trial. They did it for 12 weeks, 60 milligrams. And then they did a 20 milligram for placebo, And so the next step is basically to do a larger trial, and phase 3 trial. And so why do they do this? Well, this is for new therapies. This is AI being used as a new therapy to find some type of drug, okay? Because actually IPF is a lung tissue disease, scarring of the lung, worsening breathing and cough. And according to this, the U.S. has reported 10 to 60 people with this for every 100,000 people, okay? And supposedly rising sharply with age, okay? And the survival rate is 2 to 4 years. If you're diagnosed with IPF, supposedly your survival rate is 2 to 4 years, and the current standard of care are 2 different drugs. They kind of slowly decline, but it does not reverse it. And so there is no way of being cured from this actual disease. So IPF is something that is incurable currently. So this drug was generated to specifically focus on this therapy of IPF. It's called Rentosertib. Here is the information, the identity. You can see it's a kinase inhibitor. Phase 2 evaluated 3 dosing. So they basically gave 71 patients 3 regimens of dosing. You had 30 milligrams once a day, you had 30 milligrams twice a day, and then 60 milligrams once a day, okay? And so they just kind of did a study. Primary readouts in phase 2 included safety and tolerability and lung function. And so when you think about this, I mean, this is a research study, but, you know, it had to have a certain, you know, patients doing this. So, and as far as the biology, they consider this a critical regulator of IPF, a target described as orchestrating multiple pro-inflammatory cellular programs. Supposedly this was aimed at reducing the disease, driving programs, preserve, improve lung function. That's kind of what it's for. And this is kind of a flow of what they actually did with the drug. Why did they use it, and the target and the rationale behind it, okay? And so what I wanted to do is just kind of share this information, because this is what goes into a basic clinical trial. Of course, it's kind of small. I mean, only 128 patients, but as you can see, you know, this is something that's done totally with AI. And so how did AI contribute? Well, looking at data, literature, networks, ranking them by looking at target evidence. And this leads to something called generative chemistry, because this is what it is. Okay, you're using AI and generative AI, but it's also called generative chemistry, proposing a novel small molecule, okay, from nothing, out of thin air. And so what came next is lab validation. You have to validate the study, you have to validate what you're finding. You look at synthesis, and then you begin the phase clinical trial, which it is in now. You got phase 1, phase 2, and then they're planning on phase 3. Nothing as of yet. You can do your research on that. But AI accelerated early discovery of this, servicing as a promise in fibrosis target and generating a candidate for chemical structures to inhibit it. The candidate still required chemical synthesis, biological testing, toxicology, manufacturing, and conventional clinical trials. AI is the tool in the pipeline, not a replacement for experimental validation or regulatory evidence, which still has to be done. But this particular slide is just illustrating how AI is contributing as a real tool in the pipeline for creating new drugs. Generative AI. And so at a glance, what happened? We have participants, 71 enrolled. Where was this done? In China, 22 different sites in China. And so they had about 17 people who were given a placebo. And 3 of them were giving regimens, okay? And it was done for 12 weeks, like I said before. And we have a lot of information on key secondary endpoints, change in lung function, and a lot of different randomization. But here's the information. You can kind of look it up on your own. It's a double-blind, placebo-controlled study, and this is the way the trial has been designed. And so this is what the readout was after 12 weeks. you can take a look at this and just kind of make sense of it all as you want with the 60 milligrams versus 30 milligrams once a day in the placebo. So this is over a short time of 12 weeks. Here's another safety snapshot of phase 2 and similar overall rates. You have different treatments that was done, discontinuation by adverse events like liver injury, diarrhea. So there were some things that were discontinued because of it. So safety needs will be confirmed in larger different trials. Okay, so this was just an initial clinical trial for this drug. Okay, and so where does it stand and what's next? So this is how it started. You had AI target discovery, generative AI chemistry. You deal with phase 1 with volunteers, and then you have phase 2 with 71 patients. Phase 3 is you need a longer and bigger study, and that's where we're at right now. So it appears that AI is impactful in the front end for discovery and molecular design. Okay, so clinical success still depends on how the phase 3 trial is going to go. And the paper note that AI discovery drugs have not yet completed phase 3 in general. So we don't have any phase 3s. Yes, this is the first one. Okay, so I wanted to let you know this, and that's kind of one of the reasons why I wanted to do this slide. This is an example of what we have here. For the slide, we have different references. This is what fibrosis and scarring in the lung looks like. And then here I'm on this last page of references here. And that concludes my presentation. Thank you for watching.